Hello, everyone. Today, I will present a paper titled FDML, a collaborative machine learning framework for distributed features. And this paper is published in KDD 19. And here is the outline. I will first introduce some backgrounds of distributed feature framework, and then I will show you the problem formulation of their proposed method. We call it FDML, and the corresponding asynchronous SGD optimization method. The third part is the distributed implementation of their proposed method. And finally, I will show you the experiment results and conclude this paper. Now let's look at the background firstly. As we all know, the success of modern machine learning lays the foundation of many intelligent services, and the performance of a machine learning model often depends on the availability of the data. And in many applications, a large quantity of useful data may be generated on and held by multiple distributed parties. So for this scenario, collect such data to a centralized server for training may cause extra management and business overhead. It may also bring some privacy concerns or some other issues. That's why we need the distributed training framework. Most current distributed machine learning systems try to scale up model training by using a data parallel architecture that divides the whole dataset into several parts. As shown in this figure, we have multiple participants, and each participant will have its own dataset. All the participants will collaborate to train a global model, and each one may maintain a copy of the global model. And we call this architecture data parallel or horizontal federated learning. And for this paper, they started the distributed machine learning from a different motivation, where the information about the same samples, like the features, are owned by several parties that wish to collaborate but do not want to share the raw feature with each other. And as shown in this figure, for example, the party one or the participant one will maintain the features of the data of feature one and feature two for all the data samples. And the party two will maintain the feature three and feature four for all the data samples. So we call this architecture the vertical federated learning or model parallel, because each subset of features corresponds to a subset of the model. So we also call it model parallel. And for this architecture, the author calls them feature distributed machine learning. And let's see some practical examples of this feature distributed machine learning. Since the authors, they collaborate with the Tencent, so they use the dataset from the Tencent. They want to train an app recommendation task at Tencent My App. Tencent My App is an app store like the Google App Store or Apple App Store. So they want to train an app recommendation machine learning task. Of course, if we want to train such a machine learning task, we need some features like the app review and some download behaviors from the user. And they also want to include some other features from some other apps, like the web browsing entries from the Tencent QQ browser, some app usage information from the Tencent mobile safeguard app. So for this scenario, they train it with a feature distributed machine learning framework. Another example is that for the insurance company, if they want to train a model to provide the insurance risks of the user, they also need such a framework. Because if we want to provide insurance risk of the user, they need the insurance history from the insurance company itself. They also want some personal statistics information from the government and some patients' records from the hospital. Obviously, the government and the hospitals don't want to share this sensitive information with the insurance company. So they still need a feature distributed machine learning architecture. These are two practical scenarios or applications of this feature distributed machine learning. And for this paper, their goal is they want to train a joint machine learning model with distributed features, which will have a better prediction performance than the only local data-based architecture. And also the performance of their proposed method will approach to the performance of the centralized based training method. And in the training process, they want to minimize the information leakage, which means they want to keep the local features and the local model parameters privately. And also their method is efficient in both large numbers of features and data samples. And next, let's see the problem formulation of their proposed method and the corresponding asynchronous SGD optimization method. This is the overall architecture of their proposed model. It is a server parameter architecture. From the user point of view, we have three subsets of the input features, and each set corresponds to a local model. For example, this is the input feature of the user one, and this is the local model of the user one. This is a feature of the user two, and this is the local model of the user two. The user one's local model can be different from the user two's local model. And the only thing or the only value the user want to communicate with the server is the local prediction results. So from the server point of view, after receiving all the local results, they will generate the final output according to some functions. So this is the overview of this feature distributed machine learning model. And let's see some detailed definitions of their model. They consider m different parties and n training data samples of their training model. So we can use this vector to represent the training samples. Psi im, the vector xi im represents the features of the ith data sample in the mth party. So this is the meaning of these training samples. And the yi is the label. And we use the vector x to represent the model parameters. So xm is the local model parameters in party m. And for this machine learning, the goal of machine learning is to find a model P with parameters x and given an input data set z can predict its label y by minimizing the loss between the model prediction and its corresponding label over all training data samples. And for this prediction model, alpha is the local prediction results, and this sigma function is a continuous differentiable function. It can aggregate the local intermediate predictions alpha weighted by AG. So the final prediction P is made by merging the local intermediate results through a linear combination followed by a nonlinear transformation. And always we can set this sigma function as a softmax function. If we have, let's look at this prediction model. For this prediction model, both the local features xg and the local parameters xg and the local features psi g are stored and processed locally within this party g, and only the local prediction results alpha need to be shared to produce the final output, to produce the final prediction. And therefore, we can have our problem. We try to minimize the loss function and the regularization term. For this term is a loss function. We can use the mean square error to represent it. And for this term is a regularization term. If we have our training problem, So next step is how to solve it. Since we consider a stochastic algorithm, so let IT here be the index of the sample in iteration t, and we can rewrite the loss function as shown in this equation. We use the delta f to represent the gradient of the objective, and also we use the delta gf to represent the partial gradient of this objective. And the delta f is the concatenation of all the partial gradients. Next, we can calculate the partial gradients of this objective function. So it can be expressed in this way. The first term is a partial gradient of the regularization term. And the second term is the partial gradient of the loss function. We can calculate the mean square error firstly, and then we calculate the partial gradients of this sigma function. And finally, we will calculate the partial gradient of the local model. If we look at the first two functions of this term, this L prime function and the sigma prime function, both of these two functions contain the aggregation of all the local predictions. So we can rewrite these two functions with respect to this aggregation of the local predictions, and it can be written in this way. In this way, we use the h function times this partial gradient plus the partial gradient of the regularization term. So for this h function, we don't need the details of other model parameters, since we don't need this xk. We just need the local predictions alpha k. But if we want to calculate these partial gradients, we need the details of the xj. So this is the meaning of this partial gradient function. And if we have the partial gradient, we can use the gradient ascent method to update our model parameters as shown in this equation. And this is their asynchronous SDD method. And next, I will show you how to implement this method. What's the distributed implementation of their proposed method? The basic idea is each party G will update its own parameter xtg asynchronously, and the two parties may be in different iterations. So that's why they call it a synchronous SDD. And also they have two settings of their of this basic idea. The first setting is that they assume that different parties go through the samples in the same order, which means all the parties will share the same randomly generated sample index sequence. And this can be easily realized by sharing the same seed. So if they have the same sample index sequence, they will go through the samples in the same order. This is the first setting of their method. And for the second setting, let's look at this updating function. If we want to update the model parameters of party G in tth iteration, they need the local predictions of all of other parties. And how can we get it? So we use the local parameters of other parties to generate this output, this local output. But the training status of other parties may not locate in the same tth iteration. For example, if the training status of the party J is in the tth iteration, but the training status of other parties may not in the tth iteration. So they may locate in some other training iterations. Therefore, we use a lag term to represent these differences. This tau here represents how many iterations of a lag there are from party K to party G at the tth iteration of party G. So we use this lag term, use this tau term to represent the difference of the iteration. And also we have the second setting is that the iteration of the farthest party should not exceed the iteration of the slowest party by tau. So we have a threshold of this tau term. These are two basic settings of their method.
Yeah, I have a quick question here.
Yes.
How about the straggler? I mean, the slowest party. When they do the updates, they use the faster parties. You know, for example, if they want to do the T+1 for the slowest party, T+1 updates, so they use the old updates from the fast party.
Yes, the latest update of the fastest party. This term can be either a negative or positive value.
Oh, okay, okay.
Yes. Okay, let's move on. And let's see some details of their method. They still consider a parameter server architecture. And from the worker point of view, all the local training will be executed on the worker, which means both the forward prediction and the backward propagations are executed on the server. And the only job on the worker. And the only job of the server is to maintain and update a matrix AIG, where I is the index of the data sample or the batch sample, and the J is the index of the party or the participants. And these are introduced to this AIG matrix is introduced to hold the latest M local predictions for each sample I. For example, AIG represents the latest local predictions of data sample I in G's party. So this is the physical meaning of this AIG. And they also need the data preparation step. They need a sample coordinator, which will firstly randomly shuffle the sample indices and generate the sample presentation schedule, as we have mentioned, which indicates the order in which samples should be presented to training the algorithm. So if we have this sample presentation schedule, and all the parties will present the data in the same order. And also, if we have this sample presentation schedule, this schedule will be broadcast to this schedule with and the labels will be broadcast to all the parties. And this sample presentation schedule can be done by using some common identifiers like the user IDs or the phone numbers or the date of birth plus name or the item IDs, etc. So if we have these identifiers, we can easily generate this sample presentation schedule. And let's see the detailed training procedure of the algorithm. From the local party point of view, each party will firstly evaluate the local predictions and push it to the server. And then it will pull the latest local predictions from other parties from the server. And this value can be obtained from the matrix we are maintained. So it can be generated from the matrix AIG. And the third step is they can update the weights based on the gradient descent method. So this is what the local party will do. And from the server point of view, for the polling request, if the time index is within the threshold, then it will return the latest model predictions of all the parties from this matrix AIG. But if the time index is out of the threshold, it will reject the polling request. And for the push request, the server will collect and update the local cache, which means it will update the matrix AIG. So this is the training procedure of their proposed FDML and the corresponding asynchronous SGD method. Do you have some questions here? Okay, and also the author also derived the convergence analysis, and they have the convergence rate results, and they argue that this convergence result matches the standard convergence rate of fully centralized synchronous SGD training method with a convex loss, which means their method has the same convergence rates with the centralized based method. And next, let me show you the experiment results of their paper. Since they collaborate with Tencent, so they use the data set from the Tencent. It contains 5 million samples indicating whether a user will download an app or not. So this is a number. This is the number of the data set, data samples, and the data set contains 8,700 features in total, among which 7,000 features come from the Tencent My App, and the other features are from another 2 apps. And this is the data set setting. Let's see their experiment scenarios. They consider both logist regression and a 2-layer fully connected neural network as the local model to evaluate the effectiveness of their proposed FDML method. They consider 2 baselines. One is the local scheme, which means it only uses 7,000 local features to train the model. And the other baseline is the centralized scheme. It collects all the features from all 3 apps to a central server and execute a centralized training framework. And for their FDML method, it used the FDML system to train a joint model on all features distributed in 3 apps. So it's a feature distributed machine learning framework. And here are the experiment results. The results show that FDML outperforms the corresponding local scheme with only local features, and even approaches the performance of the centralized scheme while keeping the feature size locally. So the other side, their method can outperform the local-based method and approach the performance of the centralized method. For example, if we target on the test loss for the logist regression model, the centralized scheme outperforms the FDML scheme. But for the neural network model, the FDML scheme outperforms the centralized scheme. And the author also showed the training time of these schemes. So for both the logist regression and the neural network model, the local scheme is the fastest one, since it uses the smallest amount of features and has no communication or synchronization overhead. And for the logistic regression model, the FDML scheme is slower than the centralized scheme, since the computation load is relatively smaller in this logistic regression model, and thus the communication overhead dominates. So that's why the FDML scheme is slower than the centralized scheme. But for the neural network model, the centralized scheme is slower than the FDML scheme, since in this scenario, the computation overhead dominates, and the FDML scheme can distribute the computation overhead to 3 workers. So that's why the FDML scheme outperforms the centralized scheme in terms of the time consumption.
Here,
and this
I have
is the experiment.
Yeah,
Yeah,
I have another question. So here, basically, FDML and the centralized server, I mean, they use the same device, right? For example, centralized server, they use say RTX server, and all the FDML participants, the local agent, they use something like the RTX server as well, right?
Yes, yes. I think it should be.
Okay, so now
although they didn't mention that, but I think they should use the same type of devices.
could you explain why for the logistic regression case, the centralized better? Yeah, it's better than FDML.
Yes, they argue that since for the logistic regression model, the computation load is relatively smaller because for this it's very simple. For the logistic regression model, it's a very simple model. So the computation load is very small. But for the FDML, it needs the communication overhead. But for the centralized model, they don't have the communication overhead. So in this scenario, the communication dominates. So that's why FDML is slower than the centralized approach.
Okay, okay. I got another question. For this comparison, is that possible we can, compare with the general federated learning? It's not the feature-based distributed machine learning, it's just the general federated learning. Or just, general distributed machine learning, not feature-based one. Why don't they compare with that one?
Because here the features are distributed among all the workers, so we cannot use the traditional federated learning method to train it. For example, for the party 1, they cannot access the features of the party 2. So they cannot use the data parallel-based architecture. They can only use the feature distributed machine learning model.
Yeah, I mean, from scenario point of view, I can understand. But, yeah, that makes the experiments and the comparison much easier, actually. First of all, the local one definitely cannot beat the federal one because your data sample is much smaller, right?
Yeah, so, yes.
For centralized one, yeah, it's only 2 cases you consider here. Yeah, you can argue that, but it's really.
Hey, Doctor.
Yeah.
I want to say, like, for federated learning, there are also included 2 steps. One is for horizontal, the other one is vertical. Vertical, maybe if I remember correctly, the vertical is also feature-based something. That's because the feature will each local device have different part of the feature. So that's a lot of people work on that, focus on this kind of area.
Okay, so is there any other peer work they can compare with in the literature? Just like you said, if people work on the, say, horizontal fed learning and vertical fed learning, right? I believe there are some other existing papers in the literature for the vertical fed learning.
Yes, I think, but the case is, this paper is published in, I mean, the KDD 19, right? I mean, this is a Professor D newspaper, and there's this his group, and I remember maybe in that time, fed learning is not so much like popular than current. So maybe in that period, I mean, they don't compare with fed learning approaches. Maybe it's reasonable.
All right, please move on. Thank you.
Yes, and finally, I will conclude this paper. And in this paper, they focus on learning privately over distributed features. And they think the feature distributed machine learning is also an important problem. And their proposed FDML system can significantly outperform the model with local features and while keeping the distributed features private. And also their proposed approach their proposed scheme can also approach the performance of the centralized based approach. And that's it. And thank you.